Record. Okay, so I think we're still good. I think I'm recording now. All right. Now we're into actual physics. Measurement and estimation, which is kind of a precursor. These are just sort of numeracy skills that you guys will probably need in your physics course here, as well as probably other courses, to be honest with you. So now that that's out of the way, let's just jump right to physics. We're going to start with something called kinematics. Now, unlike, well, actually, most science-based courses have very logical names for things. I don't know about, I will not speak about other courses, but with physicists, I will say most of us are fairly illiterate. We don't read very well. Our communication skills are not very good. Our writing skills are not very good. And we speak physics and Greek better than we speak English most of the time. So we name things as straightforward as humanly possible. Just because, like, why confuse things? So kinematics, it's based on Latin, the name, and what it studies is the trajectory of a moving object. So it does not study what gets the object moving. It does not study what causes motion. It says, assuming motion already exists by some other means, some other metric, assuming motion already exists, where is it going to go? That's what kinematics is. It's the study of trajectory. So that could be something as simple as, throwing a baseball, or, landing a rocket ship on the moon, which, by the way, is a lot of other details, but a lot of kinematics as well. And many other things in between, just studying the trajectory of a moving object. So that's what kinematics is. We will, after kinematics is done, we will talk about dynamics. Dynamics is forces. Forces cause the motion. So this is just one puzzle piece in a really large scheme of things. So this is the puzzle piece we're going to start with, is assuming something is already moving, where is it going to go? There we go. So first, we're going to start our discussion with frames of reference. Okay, so we've all heard this before, maybe even a famous Einstein quote, everything's relative. Einstein is famous for the theory of relativity, of course, so you've probably heard that phrase, everything's relative. Well, specifically in this context of what we're going to be doing, motion is relative. So, at the moment, you're sitting in your room, I'm sitting in my room, we feel like we're stationary. So relative to my house, we're stationary, you're stationary relative to your house. But, if you zoom out a little bit, we're all sitting on top of the planet, and the planet is moving. So if you have a different frame of reference, we're moving all of a sudden. So motion is definitely relative. And maybe a more concrete example that you guys might be able to relate to is driving. I'm sure you've either driven a car before or been in a moving object before. When you're driving, you look at the cars on the same side of the road as you, and they're not necessarily whizzing by you. In fact, you might be keeping pace a lot of the time, and they may not even look like they're moving at all. So relative to you, other cars may not be moving on the same side of the road. But as you're driving, if you look on the other side of the road, on the left side of the road, then cars will be coming straight at you, whizzing by you. Now, presumably, if everyone's driving by the speed limit, they're coming at you at 100 kilometers per hour. You're traveling at 100 kilometers an hour forward, and the other cars on the same side of the street as you are also traveling at 100 kilometers per hour. So why is it that the cars on your side of the road don't appear to be moving when you and them are traveling at 100 kilometers per hour, while the cars on the other side of the road feel like they're whipping by you, like really fast, like way faster than 100 kilometers per hour? Meanwhile, everyone's traveling at 100 kilometers per hour. So why does it feel like one's whizzing by you and the other one is like stationary? And the answer to that is frames of reference. So here, that's more of an abstract example. A more traditional example, I guess, of frames of reference would be something like here, example 2. So let me just zoom in a little bit. So a motorboat is traveling at 8 meters per second upstream compared to the land. And the water current is 1 meter per second. How fast is the boat traveling compared to the water? Now, this is a pretty, you may have even seen this in grade 12 calculus and vectors, a question like this, that is. There's one formula we need, and it goes by different names. It could be like the frames of reference equation or the vector equation or whatever. I will write it down as most grade 12 math teachers present it to you guys, because I kind of want to piggyback on perhaps what you've seen from high school. So there's an equation that you might remember. Vector VAC, oh, oops, there we go. Vector AC equals vector AB plus vector BC. And in high school math, they teach you this equation by saying, you know, if you have a point A, I'm going to call it at the origin, and you have a point B, let's call it here, and let's say we have a point C there. Then let's say we had a vector, say we say vector AB, and we say we have a vector BC. Then if you want to add vector AB plus vector BC, then in grade 12 calculus and vectors, you're taught that you can just add vectors tip to tail. So, you know, given what I've drawn here, we have tip to tail, and then you just connect the start to the finish. So this is the resultant vector after you add the two. And you can see here that the resultant vector goes from position A to position C. So the answer is going to be V from position A to position C. And it's almost as if the insides match, then it's almost as if they cancel, and what's left is the outside. So that's kind of a tie-in from grade 12 calculus and vectors. And so that's what's going to be needed here. Now I know it's 3 o'clock, just give me 1 second, and we'll wrap up this example, then we'll wrap up the lecture for the day. So writing everything down here, a motorboat is traveling at 8 meters per second upstream compared to the land. So I'm going to say the speed of the boat compared to the ground is going to be 8 meters per second. And the speed of the water compared to the land or the ground is 1 meter per second. And we want to know how fast the boat is moving compared to the water, equals question mark. So we can follow the same equation as above. We are wanting speed of boat compared to water. So this is going to be speed of boat compared to ground plus the speed of ground compared to the water. And we set this up because the insides match, and you know, we cancel the insides and get, you know, VBW, which is what we want. So the speed of the boat compared to the ground we know is 8. And do we know the ground compared to the water? Well, no. We know the water compared to the ground. The water compared to the ground is 1. So if we want ground compared to the water, it's just the negative of that vector. So it's actually going to be -1 because, and I'm going to put this in a different color. Note that VWG equals the negative of VGW. So there we have it. Oops, I'm still in red. Let's go back to green. So overall, this is going to be 8 minus 1, which equals 7 meters per second. And this is going to be speed of boat compared to the water. Okay, so that's just an introduction to motion and an introduction to relative motion. Okay, So we're going to end the lecture there today, and well, I guess we'll resume tomorrow. So I'm going to stop the recording.